Hello everyone. Since three video lectures we have been hearing the basic concepts of optical fiber, how light travels inside the optical fiber, how they act as an essential light guide to make them travel through its optical axis, how this light waves are traveling inside this optical medium and hence support for the communication system, and what are the downside of this phenomena encountered in optical fiber, such as attenuation due to various losses and all, and types of optical fibers. You have understood all these things from previous video lectures. Now in this discussion we'll be dealing with the numericals on optical fibers, that is problems based on the concepts that you have understood so far. Now, the main idea behind this optical fiber and the communication using the light and optical fiber being the medium to transmit this light, as an information, is your total internal reflection. Total internal reflection is one of the main core topic of interest in your optical fiber. For total internal reflection to happen, the critical angle plays an important role. Now, in this session or the discussion, this is just a prerequisite for your problem solving, that is, getting to know what are the formulas and relations that are related to optical fiber concepts. The very first is critical angle. Now, generally, when light travels from one medium to another medium, basically you have refraction. This is well known concept, and you have laws of refraction as well. Now the very essential mathematical equation that governs this angle of incidence, angle of refraction, and how they behaves is Snell's law. Snell's law understands how this angle of incidence and angle of refractions plays around when the medium changes through its refractive index. Refractive index is just the optical nature of a medium where the light component slows down. In a very layman term, one can say N1 and N2, where N1 is greater than N2, N1 is denser and N2 is rarer. Denser medium means that light wave or the components of light wave takes a really long time to travel compared to rarer medium. This can be a rough explanation. But to be even more precise, geometrically you can think that when light ray travels from denser medium to rarer medium, you have this normal. Normal means that perpendicular drawn to the surface. So light bends away from the normal, and when light travels from rarer medium to denser medium, it bends towards the normal. So these are the laws of refraction, and hence Snell's law. Now the core idea behind this optical fiber is total internal reflection. As I said, we can consider this two mediums, denser medium and a rarer medium. Now N1 is greater than N2, meaning that this is denser and this is rarer. Let us consider a ray AO, falling onto this surface of the denser medium, and it is traveling from N1 to N2. N1 is a medium, denser medium, and N2 is the rarer medium. Let X dash be the boundary for this so-called medium of lower refractive index, N2, N1. Let the incident ray AO make an angle theta1. Now when AO travels through this, it makes an angle theta1, which is angle of incidence for this ray. Due to this medium that is being denser and it is traveling from denser to rarer, the refracted ray, that is OA dash, bends away from the normal, creating theta. Theta2 is a refracted angle. Due to the nature of N1 being greater than N2, this happens. If the same ray would have traveled from rarer to denser, then the game would be different. The whole refracted ray would bend towards the normal, not away from the normal. This is one of the important derivative of the Snell's law. Now everyone knows what is Snell's law. If you have two medium N1 and N2, and if you have incident radiation, that is incident angle and refracted angle, then N1 sine theta 1 is equal to N2 sine theta 2, which I have not written here. Maybe it is understood. Now, if theta 2 is the angle made by the refracted ray with the normal, then theta 2 is greater than theta 1. Let's suppose that theta 1 is increased slowly by small increment. Let's say another BO ray falls on this medium. This is the increment of the angle from theta 1 to theta 2. So when it is increased, this angle, refracted ray, or the angle of refraction, increases. Now you increase so much that this just graces, meaning that this acute angle is almost turned towards right angle. That is, theta 1 is so much increased that theta 2 becomes 90, wherein the ray just graces the surface and crosses the boundaries as per the laws of refraction. Now you can see here clearly that when theta 1 is increased, this just graces the surface. But imagine there is another ray, that is another condition, wherein you increase this angle theta 1 all the way such that it is greater than this 90, that is, the whole light ray bends back to the system. This is the concept behind the so-called optical fiber, hence total internal reflection. Now, same thing can be understood using your so-called your medium of water and air. Let's say light is traveling from water to air. Incident ray forms an angle theta 1. So refracted ray has theta 2. N1 is greater than N2 obviously, because light component slows down in water compared to air. Now when you increase this theta 1, that is your incident ray inside the water, to such an extent, that is critical angle. Critical angle means that the refracted ray just grazes the surface of the water, meaning that it is 90. The refracted ray has an angle 90 degree here, over here. Okay. So now if you increase more than that, so this angle of refraction is so much greater, creating obtuse angle. So hence, thereby you have this theta 2, which is getting back into the system. This creates total internal reflection, that is, light is not going outside, it gets trapped inside the medium. This whole idea plays important role in your optical fiber. If you consider an optical fiber as shown in the figure, so you have a core, that is empty thing over here, cylinder, that has a refractive index N1, okay, and then cladding, which is the outer surface of the optical fiber, which has N2. Here N1 and N2 is such a way that N1 is greater than N2. Now let us consider a special case where light suffers a critical incidence at the core cladding interface. Now a ray begins its journey along AO. Along AO it begins a journey, and this is your angle of incidence at the mouth or tip of optical fiber. So this is your angle of incidence of the ray at the tip of the optical fiber. Now it enters from rarer medium to denser medium. Obviously it can be water or air or any other medium apart from this N1 and N2. N1 is the refractive index of the core and N2 is the refractive index of the cladding, which you have already studied in theory. Now to have this total internal reflection, we already see that the angle of incidence, okay, is such a way that it should be as less as possible. This should be a condition for propagation. For that to happen, you see here the angle of incidence is such a way this angle of refraction is as small as possible, which becomes, so the angle of incidence over here will be 90 minus theta 1. So angle of incidence at the tip of your optical fiber is theta naught, and angle of incidence is theta 1. And angle of incidence at the interface between n1 and n2, this over here, is 90 minus theta 1. If you make this as small as possible, this grazing will happen. Even more the grazing, the whole thing light gets back into the medium, thereby traveling in this optical path. So for this to happen, the angle of incidence or angle of refraction at this point, theta 1, should be less than theta naught, which is your angle of acceptance or angle of incidence at the tip of your optical fiber. Once again, I'll repeat. This theta 1, which is angle of refraction of the optical fiber, okay, as soon as refraction takes place, should be lesser and lesser, okay, compared to that critical angle, this particular critical angle, okay, such that light enters back into the system. So thereby your angle of incidence at the interface between n1 and n2 is 90 minus theta 1. So theta 1 should be as small as possible so that light gets back into the system. Okay. The whole condition is theta 1 should be less than theta naught. Now we already know what is theta naught. Theta naught is the acceptance angle. What is acceptance angle? Acceptance angle is the angle of the waveguide. As simple as possible. If you have this cone, which is already described in the theory, okay, half of this cone angle is nothing but your acceptance angle, which is also can be said as angle of incidence at the tip of the core and the optical fiber. More this cone is more the accumulation power of this optical fiber, meaning that if you have more and more, except that you have to have the condition that critical angle is maintained. That is, angle of incidence, the angle of refraction should be as small as possible. Thereby you have all the refracted ray getting back into the system, thereby creating total internal reflection. Now through this we have this formula theta c is equal to sine inverse of n2 by n1. This is by Snell's law. You already have seen how to derive this, and we arrive at this point where theta c is equal to sine inverse of n2 by n1, where theta c is a critical angle, theta I is the angle of refraction after entering into the optical fiber, that is this over here, and theta naught is the angle of incidence at the entrance of optical fiber, otherwise known as acceptance angle. Now this forms the base for your discussion on critical angle, and hence problems calculating critical angle for any optical fiber phenomena. Now the other topic which you will quite often discuss and deal with the problems is acceptance angle. Now acceptance angle and numerical aperture are almost very close topics, because the angle at which an optical fiber accepts light entering into the system is called as acceptance angle, and sine of that angle gives you numerical aperture, as simple as possible. Now theta naught is equal to sine inverse of n1 square minus n2 square by n naught. This is the basic equation for your acceptance angle. Now what is theta naught? Theta naught is the acceptance angle. Sine inverse of n1 square. N1 square is the refractive index of the core. N2 is the refractive index of the cladding. And N1 of course is the medium's refractive index, whether it is water or air. So normally you do ideal situation, you make the light go from air to so-called your optical fiber in this manner. So N naught remains as air, hence N naught is equal to 1. If that is the case, then this whole equation will reduce to theta naught is equal to sine inverse of root of N1 square minus N2 square. Now the problems that arises for such kind of scenario will be, you calculate what is the acceptance angle for a particular optical fiber. So given N1 and N2, we can calculate theta naught easily. Of course, if the optical fiber is immersed in water or any other liquid with variable refractive indices, N naught will change. So you will be using both the equations. Only difference between these two is that a denominator N naught is the one thing which has to be multiplied. That is 1 over n naught should be multiplied or n naught should be divided. Okay, the other equation or relation you see is numerical aperture. As I said, numerical aperture is just a number, and the number will tell you what is the type of optical fiber, what is the capacity of the optical fiber. So numerical aperture is just a number, it doesn't have any unit. Sine of the acceptance angle is a numerical aperture. So basically sine of theta naught is equal to numerical aperture. Okay. So given n1 and n2 and n0, which is in ideal case air, so Na can be determined. Now you have already learned various types of optical fibers and you have seen how refractive index is variable in several cases of optical fibers. You have single mode optical fiber, you have step index, you have multi-mode step index fibers. In single mode fiber, you have a rapid increment of refractive index. In the case of step index multimode fiber, you have a rapid index but of a variable thickness. But when you go to so-called your the graded index multimode fiber, which is also called as GRIN, GRIN, you have a variable refractive index profile, and hence this delta comes into picture there. Fractional index change is the change of refractive index all the way when the light moves from n1 to n2. It can be rapid or gradual. So this relation is very important when you have to calculate the fractional index change. Delta, the change from n1 to n2, n1 minus n2 by n1. n1 and n2 are refractive index of two mediums. Now, as you have seen, the optical communication or optical fiber communication sustains, or the signal sustains in this medium only when the modes are created. That is, modes are nothing but how many amount of information is allowed. In the case of single mode fiber, only very few modes or number of light rays are allowed inside. Roughly you can translate it as amount of information. Now, as there was a small example given in the previous uh, video lectures, where there's a comparison between two channels, that is, one is optical fiber communication and the other one is electrical. We can see that the optical fiber can accommodate more number of information, more number of channel of informations. This is basically due to usage of light as a medium of information. Now for that we have very important special concept which is qualitatively studied in your case and which was V number, and which is already explained. V number will tell you what is the amount of modes or number of modes that is accommodated in a particular optical fiber. So V number is just a number, and number of modes will be given by this approximation over here. Now V number is a small number which will tell you what is the amount of information that is allowed in a particular optical fiber. V is equal to pi times d divided by lambda root of n1 square minus n2 square by n naught, where d is the thickness of the optical fiber or diameter of the optical fiber. Lambda is the wavelength of the light used. Now, there is a small approximation which you can take it as granted. For V less than 1, very much less than 1, the number of modes supported by the optical fiber is almost equivalent to V square by 2. That is, if you have V number, which is a constant, and square it and divide by 2, will give you a rough number. Those are the amount of information or channels of information that is accommodated in an optical fiber. This is one of the concept. And next we move on to attenuation coefficient. Now, as explained in the previous lectures, that this light waves or the waveguide which is accommodating these light waves or information need not necessarily be ideally traveling or perpetually going from one point to another point. There are losses that is encountered in the optical fiber due to various physical damages, impurities, macroscopic bending, microscopic bending, etc. Now these are all standardized and understood using attenuation. Attenuation coefficient is the amount of loss that is created, and how to know this loss will be spoken in terms of alpha. Now alpha is equal to minus 10 by L logarithmic to base 10 P out by P input. Now P output, P input will be the power of the light, that is P input is the light power that is entering into this point, and P output is the light that is coming out. And internally we will have various losses that is created, maybe due to absorption or microscopic bending, macroscopic bending, or due to the presence of impurities and all those. Now how much light came inside, how much left out of the system is spoken in terms of alpha. Now you see here L will always be in terms of kilometer. Okay? Please ensure that L should always be in kilometer, because the whole unit is dB per kilometer, and dB is a relative unit, so hence it's not in watt. Power is in watt, but dB is relative scale. Since we are using logarithmic 1, so we are using dB per kilometer. So L is the length of optical fiber in kilometer. P output, P input is output and input power of the light signal, which is seen here. So if you understand these amount of relations and formula, that is more than sufficient to solve problems in optical fiber.